We're going to look at an extended general equilibrium problem from the perspective of a government planner. So here we have 100 consumers, each with the utility function given by the following. X subscript 1 is units of good X consumed by each consumer. Y subscript 1 is units of good Y consumed by each consumer. So all consumers are identical. So they'll each all have the same level of consumption. X is total units of good X, and therefore total units of good X will just be 100 times X subscript 1. So there's 100 consumers multiplied by the consumption of each consumer gives us total units of good X. And likewise for good Y, capital Y is total units of good Y, and the total units of good Y is just 100. We've got 100 consumers times the consumption of a individual consumer. There are 100 units of labor. Each consumer has 1 unit of labor, and that is to be divided between 2 firms. So L subscript 1 plus L subscript 2. L subscript 1 is labor used by firm 1. L subscript 2 would be labor used by firm 2. So together, the labor used by the 2 firms must sum to 100. And so I just defined those earlier. Firm 1 has a production function. X equals 2 times the square root of labor, and firm 2's production function, firm 2 produces good Y, its production function is just the square root of labor. So first thing we're going to do, we're going to create a social utility function. This is again the government planner solution. So we're going to create a social utility function, which is going to be a function of total units of good X and good Y consumed. So we take the individual consumer's utility function, recognizing from the previous side that the total consumption of good X is just 100 times the individual's consumption of good X. And likewise for good Y, same thing. Total consumption of good Y is just 100 times the individual's consumption of good Y. So if I were to solve each one of these for the lowercase x and lowercase y, we get the following. I'm now going to substitute these 2 equations into our individual's utility function. Get something like this. And that will just simplify down to this result. Okay, 100 to this 3/4, and we got 100 down here in the denominator, the 1/4. That's just going to simplify down to 100. Next step. So our next step is we're going to create a production possibilities frontier for this economy. So we have the production function for firm 1, production function for firm 2, recognizing there's 100 units of labor to be split between those 2 firms. So the first thing we're going to do, we're going to solve this equation for labor for firm 1, just 100 minus labor to firm 2, and I'm going to plug that into X, into this equation here, into the X equation. So here's our X equation where I have L subscript 1, it's now 100 minus L subscript 2. Now we're going to square both sides. So x squared equals the following. And simplifying that up a little bit, 4 times 100 and 4 times L subscript 2. Moving on. We're going to solve here for L subscript 2, so just moving some things around from here and dividing through by 4. I'm going to take this equation, I'm going to plug it into the y equation, so where I have L subscript 2, we're going to now plug in 100 minus x squared divided by 4. Remember, L subscript 2 is being raised to the power of 1/2, so we have that here. Squaring both sides, get rid of this 1/2 up here. We get this result. Moving some things around, we have our production possibilities frontier right here. All right, so what we're going to do now is we're going to maximize the social utility function that we derived earlier, subject to the constraint, which is the production possibilities frontier, which we saw in the last slide. So this is where we're going to maximize subject to the constraint. We can set up a Lagrangian to do that. And now we're going to take a series of partial derivatives, a partial derivative of the Lagrangian with respect to x. We get this result here. And the partial derivative of the Lagrangian with respect to y. We get this result right here, setting both these partial derivatives equal to 0. And then the last partial derivative is going to be with respect to lambda, and we just get back what's in parentheses. So taking our first partial derivative, and I'm going to solve that for lambda. So moving this term right over here over to the right-hand side and solving for lambda. We get this result right here, using the rules of exponents to combine these x terms. And then that second partial derivative, the same thing. The second partial derivative that we saw on the previous slide, we're going to solve that for lambda. Moving over here, we get this result. Now we're going to set lambda equal to lambda. So our two lambda equations, this one and this one, set equal to each other. And simplify. We get this. And simplifying further, I'm going to take this now, I'm going to plug it into the constraint. So here's our constraint, or the PPF, where I have x squared. I'm going to plug in 12y squared. So x squared, what is x squared? 12y squared. And now we're going to solve for y. So just rewriting that last result, solving for y, dividing through by 4, taking a square root, y equals 5. So the total consumption of good y is 5. And since there's 100 units, 5 times 5 divided by 100 means each consumer consumes 0.05 units. And then from the last slide, we had this result. Let's see what the total consumption of good X will be in this economy. So plugging in 5 for y here and solving, the total consumption of good X is 17.32 units. So the individual, or 100 individuals, 100 consumers in this economy. So the total consumption for any given individual is just going to be 17.32 divided by 100, 0.173. Firm 2's production function is this. Firm 2 is producing 5 units, so 5 units. Y is 5 after all. So that means firm 2 will use 25 units of labor, so the government planner will allocate 25 units of labor to firm 2. And this means that firm 1, since there are 100 units of labor in all, firm 1 will be allocated 75 units. Oops, excuse me, 75 units. Okay, I hope you found this video helpful.